So we're going to discuss about a shortcut for AS arithmetic. Okay. So what is M of X? What is the AS standard M of X? M of X irreducible polynomial. Can any one of you tell me AS standard irreducible polynomial? Prime polynomial? What is the AS standard irreducible polynomial?
X power 8 plus X power 4 plus X cube plus X plus 1.
So I need to do the multiplication. Let us assume f of x, a polynomial over gf of 2 power 8. I can represent like this: x power 0 coefficient, x power 1, x power 2, and so on. Okay. So let me have the values: x power 0 indeterminate, x power 1, x power 2, x power 3, x power 4, x power 5 coefficient, x power 6, and x power 7. So there are 8 terms are there. Okay, for each term there is a coefficient. Okay, actually the coefficient either 0 or 1. Okay, either 0 or 1. There are two possible options. So that it can be b0 or it can be b1. The coefficient of x2 is b2. Coefficient of x3 is b3. Coefficient of x4 is x power 4 is b4. Coefficient of x power 5 is b5. Coefficient of x power 6 is b6 plus coefficient of x power 7 is b7. Okay, where bi is in the gf of 2. That means either 0 or 1. Okay, the values are either 0 or 1. Now let's go for a multiplication. This polynomial to be multiplied with another constant polynomial. I need to compute x into f of x. Okay, so x into f of x. Okay, so the binary equal x is also a group element of gf of 2 power 8. Okay, x is also valid group element of gf of 2 power 8 is a monic polynomial. Okay, so binary representation I can represent like this: 0 0 0 0 0 1 0. Okay, x is something but this binary number. Okay, so now I need to compute x into f of x. Okay, so if you multiply with this f of x, okay, you will get the answer like this. For example, so this will be, there will be one more new term. Okay, so x power 7 into x is x power 8, x power 6 into x is x power 7, and this determinant, indeterminant will be x power 6, and this will be x power 5, and this x power 3 into x is x power 4, x squared into x is x cube, and x power 1 into x is x squared, and x power 1 into x is x power 1. Okay, there is no x power 0 term. Okay, because it is multiplied by x. Okay, then this coefficient b7. Okay, this is actually coefficient of x power 7. Now this will become the coefficient of x power 8, because what we did, x power 7 into x. Okay, so this coefficient becomes the coefficient of b8. Okay, so this will be b7 plus this is b6, then this is b5, and this will be b4, and this coefficient will be b3, and this coefficient will be b2, and this coefficient will be b1. Now this coefficient will be b0. Okay, so now we have the resultant polynomial like this. Okay, but we have to verify that whether this polynomial is over gf of 2 power 8 or not. Okay, is it over gf of 2 power 8? Is this polynomial is over gf of 2 power 8? Is it a group element of gf of 2 power 8? Is it a group element of gf of 2 power 8? Yes or no?
No, ma'am. No.
No. Why? Because this degree is 8. Okay, the maximum degree of this polynomial is 7, never exceeds 7. Okay, so that here this x power 8 term, it's out of this field, out of this set. Okay, so if it is out of the set, what we have to do? We have to do the modular adduction with m of x. What is that m of x? That m of x is this. Okay, x power 8 plus x power 4 plus x cube plus x power 8 plus x power 4 plus x cube plus x plus 1, because this is a AS standard irreducible polynomial. Okay, so what we are doing is we are computing the shortcut for AS, so that AS standard polynomial to use for reduction. Okay, so divide this one, okay, this polynomial by this, you will get a remainder. The remainder is the actual result. Okay, so that is what the thing we have to do it right now. But remember one modular arithmetic property. Okay, so one modular arithmetic property, a mod n into b mod n, a mod n into b mod n, the whole mod n is equal to the whole mod n is equal to a into b mod n. Okay, this is a very simple modular arithmetic property. Okay, so we can exploit that modular arithmetic property here. Okay, so now this side to be matched with this. Okay, now see a into b mod n. Okay, a into b mod n. Not multiplication, addition. Okay, a mod n plus b mod n. It's applicable for addition, subtraction as well as multiplication. Okay, all these three arithmetics are available for modular reduction. So a plus b mod n. Now just a match with this polynomial. Okay, a plus b mod n. Okay, so what we are going to do here is this polynomial is a plus b polynomial. Okay, I have to split it into two polynomials. Okay, so let it be this part is a, this part alone is a. Okay, so plus this part alone is b. Okay, now this is in the form a plus b mod n. N is m of x. Okay, so here a is a polynomial, b is a polynomial, n is also a polynomial. Okay, so a is this and b is this and n is m of x. Okay, so if it is so, I can expand like this. Okay, so we can do it like this. A mod n, so this is a. Okay, so that I can rewrite this as b7 into x power 8 mod m of x. A is standard irreducible polynomial because this is n. Okay, this is n, you know. So this part is matched with a and this part is matched with b and this part is matched with n. Okay, so b7 into x power 8 mod m of x plus. Okay, now replace substitute this b. Okay, what is b? This entire part. Okay, so b6 into x power 7. Okay, I will write it out in the different colors so that you can better understand this. Let it be, this is b6 into x power 7. This is a different term. Okay, so b6 into x power 7 plus b5 into x power 6 plus b4 into x power 5 plus b3 into x power 4 plus b2 into x cube plus b1 into x squared plus b0 into x or x power 1. Okay, so the whole thing mod m of x. So this is b. Okay, this term is b. So just observe this. This is a and this is b. Okay, so a is already the degree is 7. Okay, already the maximum degree is 7. Okay, this is a polynomial with the degree is 7. Okay, so this is already reduced polynomial. Okay, no need to do the model reduction with m of x. Okay, because this polynomial already is a group element of m of x. Okay, if you divide by m of x, you will get the same remainder. Okay, if you divide this by m of x, you will get the same remainder. This will be the remainder. Okay, so that b mod m of x itself is b. Okay, no need to do the division at all. Okay, but take it out this part. Okay, this x power 8 is a monic polynomial with a degree greater than the gf of 2 power 3 maximum degree. Sorry, gf of 2 power 8 maximum degree. So for this alone, you have to do the model reduction. You have to do the reduction, division. Okay, you have to perform the division. So the last class we did the division. Okay, can you remember the last class content? Okay, I will show it in the whiteboard. Just to remember this part. See, x power 8 mod x power 8 plus x power 4 plus s cube plus x plus 1. Okay, if you divide it, I just we divided and we got the remainder. What is the remainder? X power 4 plus x cube plus x plus 1. Okay, take it out the box content and load. X power 8 mod x power 8 plus x power 4 plus x cube plus x plus 1 is x power 4 plus x cube plus x plus 1. Okay, so this monopolynomial can be reduced like this. Okay, so we did the division and we got the remainder. The remainder is a resultant theta. Okay, have you taken this component? A reduction of monic polynomial. Okay. Now just to come back. Okay. If this term is non-zero term, definitely B7 will be 1. Okay, B7 is 1. So 1 into x48 mod m of x. What is answer? What is answer? This alone, x48 mod m of x. If B7 is 1. Okay. So what is x48 mod m of x? M of x is a standard polynomial x48 plus x44 plus x cube plus x plus 1. What is the result of this? What is the result of this? Divided, what is the remainder? Students, can you able to follow me? X48 mod x48 plus x44 plus x cube plus x plus 1. What is the remainder? I have shown in the previous slide, no? What is the remainder?
X power
When
4
you
plus
divide
x
it, what is
cube
the
plus x
remainder?
plus 1.
X power 4 plus x cube plus x plus 1. So this part alone to be reduced like this. Okay. Plus, this is a simple polynomial. This is already reduced because mod m of x, this degree is 7. Okay. So already the degree is 7. So after reducing the polynomial, you will get it like this. B6 into x power 7 plus B5 into x power 6 plus B4 into x power 5. Then B3. Here I have omitted B7, but here I am adding. Okay, for simple reason, I will tell you x power 4 plus B2 into x power 3 plus B1 into x power 2 plus B0 into x power 1. Okay, so this addition, GF of 2 point of view, this addition is simply an XOR. Okay, this addition is simply GF of 2 addition, you know. So this addition is an XOR operation. Okay, so x power 8 mod m of x can be reduced like this. Now the remaining term can be reduced like this. So x into f of x into f of x is this. Okay, so what is this? This is actually a simple shifting. Okay, so the B0 bit is shifted to the left, B1 bit is shifted. So this is a shift operation, single shift operation. Okay, followed by one XOR operation with this binary pattern. Okay, so x power 0 term, x power 1 term, x power 2 term is 0, x power 3 term is 1, x power 4 term is 1. Okay, so this bit to be XOR with this bit pattern. Okay, so x into f of x is simply, okay, so if you want to multiply x into f of x to be multiplied with x into f of x, the final conclusion here is, in the f of x, in this f of x, if b7th bit, that is the most significant bit, or otherwise I can write it out like this, the most significant bit of this f of x, if is equal to 0, then x into f of x is nothing but x into f of x is nothing but simple shift operation. Okay, a left shift. Otherwise, okay, if B7 bit is equal to 1, okay, the most significant bit is equal to 1. If it is so, then x into f of x is nothing but, okay, we have to do the shifting. Shifting is also required. Okay, so a shift followed by an XOR operation with a binary bit pattern 110110, sorry, 11011. Okay, so this is a thumb rule here. Okay, just see this, just take it out this. Okay, the entire derivation is for this particular rule. Okay, so what is the rule here? In the f of x, the polynomial, okay, so in this f of x, first of all, check the polynomial. Okay, the most significant bit, if it is 0, x into f of x is simply a shift. Okay, if the most significant bit is 1, then do the shifting followed by and a simple XOR. Okay, so this is what the simplification of x into f of x. In the similar manner, we can derive the simplification for x squared into f of x cube into f of x power 4 into f of x. Okay, before getting into x squared and f of x, let's go for an example here. Let's take a simple example. I need to multiply. Okay, I need to multiply x with f of x. Okay, let it be the f of x is the polynomial representation of 8, 7. Okay, so first of all, represent this 8, 7 in terms of polynomial. Okay, or otherwise in the terms of binary, because it's based on shift operation or XOR operation, everything is in terms of binary. Okay, represent in terms of binary. Okay, so 8 to be represented in terms of binary. Okay, 1, 0, 0, 0. 7 represent in terms of binary, so 0, 1, 1, 1. Okay, so this one to be multiplied with x. Okay, now I have represent this in terms of hexadecimal. Okay, okay, so this can also be, x can also be represented in terms of hexadecimal. What is the hexadecimal equivalent of x? What is the hexadecimal equivalent of x? Hexadecimal representation of the polynomial x. What is the hexadecimal representation of the polynomial x? This is x, and this is x power 7 plus x squared plus x plus 1. Okay, x power plus 1 plus x squared plus x plus 1 is represented like this, 8, 7, and x to be represented in terms of hexadecimal number. Okay, so what is the equivalent hexadecimal number for this? X to be represented. What is
0,
it?
2.
Good. 0, 2. So now 0 to multiply with 8, 7. Okay, if you have the element representation like this is not a normal number. These are the polynomial representation of binary decimal numbers. Okay, sorry, hexadecimal numbers. So actually, what we have to do, the x to be multiplied with f of x. F of x is x power 7 plus x square plus x plus 1. Okay, x power 7 plus x square plus x plus 1 is represented in terms of hexadecimal, it's 7, and x is represented in terms of hexadecimal, 0. Okay, now actually my operation is, required operation is 0, 2 into 8, 7. Okay, so simply check the most significant bit. Okay, so what is the most significant bit? Here the most significant bit is 1. Okay, if the most significant bit is 1, two operations are required. One is a shift and then XOR. Okay, just to do the shifting here, shift 0, 0, 0. So this bit will be shifted here. 1, 1, 1. This is not a circular shift. This is a shift. Okay, so this term will be 0. Okay, the padding bits are normally filled with 0. So this will be 0. Okay, so the most significant bit is 1. So that two operations are required. The first operation is shifting. We did shifting, followed by XOR. XOR with 1, 1, 0, 1, 1. Okay, so 1, 1, 0, 1, 1. Okay, just to do the XOR, the result is 0, 0, 0, 1, 0, 1, 0, 1. Okay, so now its equivalent hexadecimal representation is, this is 1. Okay, this is 1, comma 101. So 101 is 5, not comma. Okay, so you need not use comma here. So this is nothing but 1, 5. Okay, so 0, 2 into 8, 7 is 1, 5. Can you understand this concept? If the most significant bit is 0, this operation is not required. XOR operation is not required. Simply a shift operation. Okay, so multiplication by 2, but previously without this shortcut we need to multiply these two polynomial. Definitely the resultant polynomial will exceed the degree, because 8, 7, 8 power x power 7, if it is multiplied with x, you will get x power 8 term. Okay, so you have to reduce it by doing division. So one multiplication, polynomial multiplication followed by one polynomial division is required, but here it is simplified as one shifting and one XOR. Okay, clear? Clear? Is it clear? Students? Okay, so slightly we move on to the subsequent shortcut. Okay, so I need to do this another component called 0, 3 into 6. Okay, both are polynomial over gf of 2 power 8. Okay, so let us represent this as, this is nothing but 0, 0, 0, 0, 0, 0, 1, 1. Okay, so this is x plus 1. This polynomial is x plus 1. This polynomial is 6. So this will be converted into binary. So 0, 1, 1, 0, E is 1, 0, 1, 1. So this polynomial is x power 6 plus x power 5. So this is x power 4 term. So this is x power 3 term, x power 3 and the 2, 1. Okay, so we need to multiply x plus 1 into this. Now what is the shortcut? Okay, how to do this? Okay, any idea? Any guess? Actually, we are going to exploit this the same thing. Okay, 0 2, the same rule. Only one rule is available. The same rule to be reused. Okay, is there any shortcut to do this? 0e into x 6 power e, sorry 6e without polynomial multiplication, polynomial division. I have to solve this. Any guess? Any guess about this? How can I do this?
E is 1110, ma'am.
Is oh 110. Now this one should be x power 5, x power 3, x square plus 6. X square. Is it correct now?
Yes, ma'am.
Okay. Now tell me 0 3 into 60. Any shortcut for this? Any shortcut for this? By exploiting the same rule. How can I solve this? Without
Left shift 3
polynomial
times.
left shift.
3 times.
Okay. Okay. Let it be instead of this polynomial. I have let us assume I have integer. Okay, that should be multiplied by 3. Okay, multiplication by 2 is a shifter. Okay, I need to represent in terms of shifting operation. Any 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 guess here? How can I represent this 3a? Can I represent like this? 3a is equal to 2a plus a. Okay, so 2a, you know the shortcut, shift followed by option XOR. Okay, addition is not actually addition. In GF of 248, what is actually addition? Addition is also an XOR operation. So 3a, this operation, okay, it can be implemented, executed by using one shift followed by one XOR and one option XOR. That's it. Okay, so 3a is equal to 2a plus a. I can write like this. Okay, I'm going to exploit the same thing here. So 0 3 is nothing but 0 2. Okay, that is multiplied with the 6e. Okay, so here multiplication 2 into a, so multiplication, and plus here the plus is XOR operation plus a. Okay, so a is 6e. I can expand like this: 0 2 into 6e XOR with 6e. Okay, now multiplication by 2 is a rule. We have a simple, we have a derived that rule. One is shift followed by option XOR. Okay, now represent this 6e. What is 6e? 6e is 0 1 1 0 1 1 1 0. So this is 6e. Okay, so multiplication by 2 is shift followed by option XOR. Okay, check it out. This bit, the most significant bit is 0 now. Okay, if the most significant bit is 0, then the multiplication by 2 is simply a shift. Okay, now do the shifting 1 1 0 1 1 1 0 0. Okay, so now this is over. Multiplication by 2 is over. Now that should be XOR with the 6e. Okay, so 6e is here. Multiplication by 2 is already here. Just to do the XOR. Okay, 1 0 1 1 1 0 1 1 followed by, so this will be 0 0 1 0. Okay, so 1 0 1 1, this is nothing but b. Okay, and 0 0 1 0. Okay, so this is equal to b2. Okay, so here also number of operations are shift followed by next one. Okay, shift followed by next operation. Okay, so can you understand the multiplication by 2 and multiplication by 3? Students, can you understand this? multiplication of the GF of 248 polynomial with 2, multiplication of GF of 248 polynomial with 3. Okay, so multiplication by x shorted and multiplication by x plus 1. Okay, can you understand this too? Can you understand these two things? Okay, so this is one example. Okay, let me take this portion separately. This is one example and this is another example. Okay, so let's go further. 0 to 03 we did. Okay, let me take another example. Okay, I need to multiply 0e. Okay, let me take a large number. Is somewhat a larger number as compared to 03. I need to multiply with 0e with a GF of 248 polynomial. 0e. Okay, 0e to be multiplied with. I'll take a book sample here. 0e to be multiplied with 4 7. Okay, 0e to be multiplied with 4 7. Okay, how can I do this? Any guess? Any idea here? First of all, I'm going to represent this in terms of binary. So this is 0 0 0 0. So this is 1 1 1 0. Okay, so 4 0 1 0 0 0 1 1 1. Okay, so now the 4 7 polynomial to be multiplied with 0. Okay, how can I do this? How should I do this? Just to take it out this alone. Okay, so 0 0 0 0 and 1 1 1 0. Okay, so what we have to do here is this 1 0 first time you have to multiply with 4 7 to be multiplied with the 2, so that you will get, okay, so just a 4 7 to be multiplied with the 2, so that you will get 0 0 1 0. Okay, if it is multiplied with the 2, then you have to do the shift and XOR operation, you will get the result. Multiplication by 2, you know, the shift followed by simple XOR. Okay, after multiplication by 2, you will get the results. Okay, so that can also be shifted and you can do the XOR operation. If the term is, if it is multiplied by x, you will get 0 0 0 0 0 1 0 0. Okay, so again the resultant term to be multiplied with x, you will get 0 0 0 0 1 0 0 0. Okay, now you will get three different polynomial. Okay, just do the XOR with these three polynomial, you will get 0 0 0 0 1 1 1 0. So this is exactly the same thing. Okay, so I'll do it. Okay, let's get into this. 4 7. Okay, 0 1 0 0 0 1 1. Let's take this polynomial. Okay, I will erase it because seems to be redundant. Okay, now take it out. 4 7. Okay, 4 7 is 0 1 0 0. So this is 4 7. Okay, so 0 1 0 0 0 1 1 1. Okay, so just I'm going to multiply this with 0 2. Okay, so binary representation of 0 2 is 0 0 0 0 1 0. Okay, so what is the operation here? Check it out. The most significant bit. The most significant bit is 0. So the result is simply a shift. Okay, so the result is 1 0 0 0 1 1 1 0. So shift of this. Okay, so multiplication by 2 I did. So now the 4 7 to be multiplied by 4. Okay, you just take it out this. Okay, 1 0 0 0 1 1 1 0. Okay, so when you multiply this by 2, you will get the result in polynomial. Okay, so when it is multiplied by 2, Okay, so this is multiplication by 0, 2. Okay, now this is multiplication by 0, 4. Okay, now here I'm going to multiply by 2. So 0, 0, 0, 1, 0, 0. So this is actually 4. Okay, so this resultant polynomial to be multiplied by 2. Okay, sir, not 4. Sorry, this is multiplied by, this one should be multiplied by 2. Okay, because it is already multiplied by 2, you know. So this is already multiplied by 2. Now again this is multiplied by 2. So this is multiplication by 4. Okay, so by multiplication by 2 is a simple shift operation. So let's check it out the most significant bits. Now the most significant bit is 1 here. So you need to do 2 operation. One is the shifting followed by extra. Okay, just to do the shifting first. So shift is 0, 0, 0, 1. Okay, then 1, 1, 0, 0. So this is the result of shift followed by XOR, because this is the most significant bit is 1. Okay, so XOR with 1, 1, 0, 1, 1. X power 4 plus x cube plus x plus 1. Okay, just to do the XOR with this, because the most significant bit is 1. Okay, so the result is 0, 0, 0, 0. So this will be 0, 1, 1, 1. Okay, so actually most significant bits are 0, then the subsequent operation it won't require any additional XOR. Okay, so 0, 0, 0, 0, 0, and this 1 XOR 1 is 0, 1 XOR 1 is 1, so this is the 1. Now this one to be multiplied by again 2. Okay, if it is multiplied by 2, you will get the effect of 4, 7 multiplication by 8. Okay, so 4, 7 multiplication by 8. So take it out this. So 0, 0, 0, 0, 0, triple 1. Okay, so we have to multiply by 2. So 0, 0, 0, 0, 0, 0, 1, 0. So simply shift, because the most significant bit is 0 here. So it's simply a shift. So 0, 0, 0, 0, 4 zeros, 3 ones. Okay, 4 zeros, 3, 1 ended with a 0. Okay, so now we got the result for multiplication by 2, multiplication by 4, multiplication by 8. Okay, but what we need to do here is we need to multiply with 1, 1, 1. Okay, 1, 1, 1, 0. Okay, we have to multiply with, okay, I will write it out. Okay, 0e is nothing but 0e. Its binary equivalent is 1, 1, 1, 0. Okay, 1, 1, 1, 0. So this can be expanded as 1, 0, 0, 0. Okay, XOR with 0, 1, 0, 0. XOR with 1, 0. So 0, 0, 1, 0. Okay, so what is the answer here? We have to do the XOR operation. Okay, so just to take it out all the answer together. Okay, now here the result is, take it out this is multiplication by 2, this term. So the result is here, is it 1 or 0? 1 balance. Okay, so multiplication by 2 is 1, 0, 0, 1, 1, 0. So this is multiplication by 2, 1, 0. Then multiplication by 4, you just take it out this. Multiplication by 4 is 0, 0, 0, 0, 0, 1, 1. Okay, that correctly. So this is triple 1, 0, and this is 0, triple 1. Okay, so this is multiplication by 0, 0, 1, 0, and this is multiplication by 0, 1, 0, 0. Okay, now we need to do, we have to add the final element, that is multiplication by 8. Okay, so multiplication by 8 is this. So this is 1, 0, 0, 0. Okay, so this is 0, 0, 0, 0, 1, 1, 1, 0. XOR is just to count number of ones. The number of ones is equal to even, then 0, otherwise 1. So here the result is 1, then 0, 0, 0. Now here 2, 1. 1 XOR 1 is 0, and here 3, 1. So 1. Here also 3, 1. So the result is 1. Here we have 1, 1. The result is 1. The final result is 8 followed by 7. Actually, what I did is, actually these examples are required for tomorrow's class. Okay, so tomorrow class we have to multiply by 2, multiply by 3, multiply by 1, we have to multiply by E, and we have to multiply by B. Okay, actually for multiplication by 2 I have taken this 8A as a input. Okay, now this is good, correct only, 8A is record proper. Okay, so 02 into 47, 04 into 47, and 08 into 47, just add all together, that will be 0E into 47. Okay, can you observe this? Can you understand this concept clearly? Mixed column rounds, for a single mixed column rounds, total number of multiplication required for completing a single mixed column round is 16 multiplication. Okay, so without shortcut, it is not possible to complete mixed column rounds. Okay, so mixed column round, you have to exploit simplification. Then only you can solve this problem. Okay, can you understand this shortcut clearly? Everything is based on a simple logic. Check it out, the most significant bit. If the most significant bit is 1, shift followed by extra. If the most significant before a shift, okay? And if the most significant bit is 1, shift followed by extra. Okay, so that logic is based on the polynomial addition property. Students, clear? Can you understand the concept? Any doubts so far? Or you having any doubt? Can you understand multiplication by 2, multiplication by 3, multiplication by E? Actually, we need to multiply by E, D, 2, 3, and so on. Because the mixed column round is based on GF of 2 power 4 polynomial ring. Okay, GF of 2 power 4 polynomial ring. So multiplication by a polynomial with a degree 4 is required. Okay, so we need to frequently multiply the GF of 2 power 8 polynomial with 0, 2, 0, 3, 0E, and 0D. Okay, clear? Any doubt in this? Students, tell me yes or no. Any one of you please respond to me.
No doubts, ma'am.
Okay, good. So all these are prerequisite for mixed column. Okay, so now only we are getting into the mixed column round directly. Okay, so we have just half an hour more. So let's start with the mixed column rounds. Okay, so it's a column wise transformation. Okay, so it's a column wise transformation. Column wise transformation. Subide round is a cell wise transformation. Okay, but here this is a column wise transformation. Okay, let's go for the mixed column round. So the mixed column round, its equivalent reverse transformation is the inverse mixed column. Okay, so let's proceed with the mixed column. So this is based on a polynomial ring over GF of 2 power 8, oh, sorry, GF of 2 power 4, polynomial ring over GF of 2 power 4. Okay, polynomial ring. Okay, so I think we have already discussed about the parameter or operation related to polynomial ring. Okay, so polynomial ring, what is actually polynomial ring? The coefficient reduction should be over GF of 2 power 8. Okay, the entire polynomial ring reduction should be over GF of 2 power 4. Okay, so that problem, that example we did already. So GF of 2 power 8 polynomial ring with a prime polynomial for this is x power 4 plus 1. Okay, so x power 4 plus 1. So mixed column is constructed based on a simple polynomial. Okay, 0 power 0. Okay, see, we have a polynomial f(x). Okay, polynomial ring is represented like this. f(x) is equal to, has 4 terms. Okay, x power 3 term, x power 2 term, x power 1 term, and x power 0 term. All these are indeterminate. And all the coefficients are polynomials. Okay, all the coefficient of this is over GF of 2 power 4 polynomial ring. Okay, all the coefficients are over GF of 2 power 8 AS standard irreducible polynomial. Okay, so the coefficients are, so this is actually 0, 3, okay, and added with 0, 1, okay, added with, okay, I'll tell you how we got these 0, 3, 0, 1. I'll tell you. This is based on a simple theorem. Plus 0, 2. Okay. So this is a base behind the mixed column round. Okay. But understand this, because this A of x is not a polynomial. A of x is a polynomial ring. Okay. Polynomial is different from polynomial ring. Okay. In polynomial ring, the coefficient reduction should be over GF of 2 power 8 arithmetic. Okay. That's why it is represented in the different form. Okay. So AS mixed column round is based on this polynomial ring 0, 3 into x cube plus 0, 1 into x square plus 0, 1 into x power 1, 0, 2 into x power 0, where 0, 3, 0, 1, 0, 1, 0, 2, all these are polynomial over GF of 2 power 8 with m of x power 8 plus m of x power 4 plus x cube plus x plus 1. Okay, so now the operation is in the mixed column round. Remember, in AS, each intermediate data is represented as state array. State array. Okay. So what is state array? So state array is a 4 by 4 matrix. Okay. Let's take one example here. Yeah, I will take it out our book example for state array. So this is actually a simple state array. First byte, actually we have to fill it in the column wise manner. I think you can remember this way of filling the state array. State array to be filled in the column wise manner. Okay, the state array to be filled in the column wise, not in the row major order. Okay, row major order is a default option for filling the matrix in the programming language, but in AS, column major order to be used. Okay, so the concept is, let us assume I have the input for the mixed column round as like this: 8, 7, 6, E, 4, 6, A6. Okay, all these values are not random value, these are the book values. Okay, let me take it out the same book values. 2, 4C, E7, all these are polynomial over GF of 2 power 8. Okay, so 4D, 90, and 4A, D8, okay, 97, EC, then C3, 95. Hey, this is a state array or input to the mixed column round. Okay, so remember, for sub-byte round, the operation to be applied for each and every byte of data, each and every cell of the state array. Okay, and shift row operation to be applied for each and every row. So we have 4 rows, so 4 times the operation to be repeated. Shift row. So mixed column, it should be repeated for each column. There are 4 columns in the state array. So the operation to be repeated for 4 times. Okay. So first you have to take it out, the first column alone. Okay. The first column alone, and we have to just transform it. Okay. We have to apply mixed column round for every column separately. Okay. So let us concentrate on the first column. Okay. What is a column? It's a column vector. Take it out the column vector. 8, 7, 6E, 4, 6, and 8, 6. That column, and just now I'm going to represent that column as a column vector. The column to be transformed to a transformed column C prime. Okay, so mixed column round to be applied for every column. Okay, so there are 4 columns. So the 4 times the operation to be repeated. Okay, so what is actually operation? This column vector to be represented as the polynomial ring. Okay, that means B of x. Okay, so this A of x to be multiplied with this B of x. Okay, so I need to find out D of x, the resultant polynomial, that is equal to A of x, where A of x is a polynomial ring over GF of 2 power 8. That one to be multiplied with B of x. B of x is also a polynomial ring over GF of 2 power 4. Okay, so can you remember the final derivation of this D of x formula? I think lesson number 10, we derived the final shortcut for this matrix multiplication. Okay, this polynomial ring multiplication in terms of matrix multiplication. Can you remember? Can any one of you can remember the formula? Can you remember the matrix multiplication operation? Can any one of you just dictate the matrix multiplication operation? We did a shortcut for this polynomial ring multiplication. Okay, we just converted this polynomial ring multiplication into a matrix multiplication. Can you remember that matrix multiplication? So D0, D0, D1, D2, D3. So which is equal to, what is a matrix here? A of x coefficient to be represented as matrix. Can you tell me the first row? Can any one of you tell me the first row of this?
A0,
A0,
A3, A2, A1.
then subsequent.
A1, A0, A3, A2.
Good. Actually, you need to remember that's shifting. Then next one.
A2, A1, A0, A3.
Okay, good. Final row.
A3, A2, A1,
A1.
A0.
Okay, good.
A0.
Thank you. So this one to be multiplied with this matrix. So this will be D0, D1, D2, D3. Okay, just remember this matrix. Okay, what is actually A0? A0 is the coefficient of x power 0. Okay, A3 is a coefficient of x3. Okay, A2 is a coefficient of x2 and A1 is a coefficient of x1. Okay, sorry, x power, all these are power, sorry. So this is actually a coefficient of x power 0 and this is a coefficient of x power 3, this is a coefficient of x power 2 and this is a coefficient of x power 1. Okay, so just see, I'm going to represent this multiplication, that is a of x. Please make it out because the screen is not visible to me. So a of x, 0 power 3 into x power 3, 0 power 2 into x, sorry, 0 1 into x power 2, 0 1 into x power 1 plus 0 2 into x power 0. Okay, so this is nothing but this term is a0. Okay, coefficient of x power 0. So this is a1 and this is actually a2 and this is a3. Okay, now fill all these a's value coefficients by using this term. Okay, these terms. A0 is nothing but 0 2, A1 0 1, A2 0 1, A3 0 3. Okay, can any one of you substitute this? Tell me the answer. Okay, so this can be, I can represent this as D0, D1, D2, D3. This result is equal to A0. What is A0 here? What is A0? X power 0 coefficient in this A of x. Mixed column A of x. What is the x power 0 coefficient here? What is the x power 0 coefficient? What is the x power 0 coefficient here?
Not 2, ma'am.
0, 2. Okay, just substitute it. X power 0 coefficient is 0, 2 followed by x power 3 coefficient. What is x power 3 coefficient? What is x power 3 coefficient?
0, 3.
0, 3. X power 2 coefficient?
0, 1.
This is x 0, 1. So x power 2 coefficient and x power 1 coefficient. X power 1, this is x power 2 coefficient and x power 1 coefficient. Both are 0. Okay. So now the subsequent value can be filled based on a shifting. Okay, because we know the rule here. So 0, 2, 0, 3, 0, 1. This is a matrix. Okay, the constant matrix. You need not remember the matrix. Okay, AES algorithm, nothing need to be remembered. Okay, everything is based on derivation. If you know the funda, then you can solve it easily. Okay, you need not remember anything. Okay, so 0, 2, 0, 3, 0, 1, 0, 1. What is the subsequent row? Subsequent row is simply a shift. Okay, So this will be 0, 2, 0, 3, 0, 1, 0, 1. Okay. Now this will be 0, 2, 0, 3, 0, 1, 0, 1. Okay. Now this will be 0, 2. Okay. Now 0, 3, 0, 1, 0, 1. Okay. So this, all these are not normal coefficient. All these are polynomials. All these are polynomials over gf of 2 power 8. All these are polynomial over gf of 2 power 8. Okay. So this one to be represented like this. Okay. All these coefficients are polynomial over gf of 2 power 8. So represent by using a set symbol. Okay. Now this matrix to be multiplied with the column matrix. Okay. So take it out the first column alone. Okay. See, first column. What is the first column in the state array? See, we have taken the first column as 8, 7, 6E, 4, 6 is 6. Okay. One column to be transformed first. Okay. Column wise transformation. So the first column to be transformed. Okay. 8, 7, 6E. Okay. Just multiply with 8, 7. Okay. So this one to be multiplied with. Okay. What is the column vector? First column 8, 7, 6E, 4, 6 is 6. Okay. So this one to be multiplied with the column vector. This is 4 by 4 matrix. This is 4 by 1 matrix. So that you will get the resultant matrix as 4 by 1. Okay. You will get a column vector as answer. Okay. The transformed column vector will be the answer. Okay. So now to perform this, because this 0, 2 is a polynomial over gf of 2 power 8. Okay. And this 8, 7 is also polynomial over gf of 2 power 8. Okay. So to find out the first element, what we have to do? You just take it out the first row, first column, 0, 2 into 8, 7, 0, 3 into 6e, 0, 1 into 4, 6, 0, 1 into 4, 6. This is what the operation you require. Okay. So let's go for only one element calculation because I have 2-3 minutes more. Let's go for only one element. Okay. So the first element 0, 2, okay, multiplied with 8, 7 plus, okay. So we are computing the first element alone. Okay. So that is D0. So D0 is equal to D0 is equal to 0, 2 into 8, 7 and then 0, 3 into 6e. Okay. Then 0, 1 into 4, 6 plus 0, 1 into 6. That's it. Okay. 87 multiplied by 2, we did already. What is the answer? What is the answer for this? We did already. What is the answer? We did the beginning of the class. What is the answer? What is the answer? 0, 2 into 8, 7. Any one of you have taken notes? What is the answer? 0, 2 into 8, 7. We did the beginning of the class. What is the answer? Anybody have the answer for 1, 5? Okay. And 0, 3 into 6e? 0, 3 into 6e? 0, 3 B 2. Okay. Plus this is multiplied by 1. Multiplied by 1 is exactly same, you know. Okay. So this is actually 4, 6. And this is also all the addition operations are extra because this is GF of 2 power 8. Okay. So this is 6. Okay. What is the final answer? Final answer is XOR of all these values. Okay. XOR of all these values, that is 0, 0, 0, 1, 1, 0, sorry, 0, 1, 0, 1. Okay. 1, 5. Okay. I have represented 1, 5 like this. Okay. And then B2. B2 is 1, 0, 1, 1. Then 0, 0, 1, 0. Okay. Then 4, 6. So 4, 6 is 0, 1, 0, 0, 0, 1, 0, 1. Okay. Sorry, 1, 1, 0. 1, 1, 0. Okay. Am I correct? Can you able to follow me? Then finally A6. Okay. So take it out the A6. A6 is 1, 0, 1, 0. A is 1, 0, 1, 0. So this is 0, 1, 1, 0. Just do the XOR. So 2 ones are here, so the result is 0. Here only 1 1, so result is 1. So here 2 ones, so 0. 1 XOR 1, 0. And here all zeros, and here 1 1, and 3 ones here, so the result is 1 and 1. Okay, so what is this? This is nothing but 4 7. Okay, so the first number is, okay, this D0 is for 7. Okay, we have computed D0. So D0 is 4 7. Okay, similarly compute D1, D2, D3. What is D1? D1 is the second row, this column. 0 1 into 8 7 plus 0 2 into 60 plus 0 3 into 4 6 plus 0 1 into 8 6. Similarly compute D3 and D2. Okay, so in this way, to solve one column, to find out one column in the AS algorithm, you need to do that arithmetic like this. Okay, so every time when you do multiplication and then division, then it will be a time constant. Okay, so that's why the shortcut is available here. So all the operations are shifting and XOR. Okay, so number of so many shifts followed by optional number of XOR. Okay, can you solve the remaining element? Can you find out D1, D2, D3? So when you come for tomorrow's class, complete this entire matrix. Okay, so this is one column. Complete the same operation for the second column, third column, and fourth column. Okay, so this is actually a mixed column operation. Tomorrow we are going to discuss about inverse mixed column operation. Okay, so we have to recover back this column from the transformed column. Okay, so complete this column and find out the answer. Okay, apply the same principle for the each and every column and come with a transformed stator. Okay, tomorrow we'll apply inverse mixed column. Okay, tomorrow we'll discuss about inverse mixed column. In forward transformation, we have to apply mixed column round. In reverse transformation, inverse mixed column round. Clear? Any doubts?